Okay, hi everyone. This is TCS seminar at the Jagiellonian University. Our second speaker today is Robert Hickingbotham from, Robert finished PhD in Monash under supervision of David Wood. Now he's a postdoc in France, in Lyon, working with Édouard Bonnet. We shouldn't go further with our French within this audience, I think. We're happy to have you here, Robert, and looking forward to hear, a mix of coarse graph theory and non-coarse.
Yes, all coarse graph theory related. So yes, thank you very much for having me. So as part of my postdoc, I've been thinking about coarse graph theory. I'll be sharing some new results and progress in this direction. So my background is in graph minor theory, and that is sort of what graph minor theory is a very beautiful area of graph theory, but it has limitations in that it only applies to sparse graph classes. And so what I'm interested in understanding, how can we take graph minor theory and extend it to new graph classes? And so that's what led me to my interest in coarse graph theory. Now, just judging by the audience, I think most people here should have some decent understanding of graph minor theory. So I'm going to be going over that part relatively quickly, but spending more time about the coarse stuff, because usually in these audiences, that's what people get really caught up with. So let me begin with a brief overview of graph minor theory. So what is a minor of a graph? A graph H is a minor of a graph G if we can obtain H from G by deleting vertices, delineating edges, and contracting edges. Or equivalently, we can think of a graph H as a minor of a graph G if in H we have a collection of disjoint connected subgraphs, and each of those corresponding to a vertex in our minor H, where two of these connected subgraphs are adjacent whenever there is a corresponding edge in H. So here we've got H, we've got G, we've got these four connected subgraphs, we've got four connected subgraphs. H is complete graph in four vertices, so each of these connected subgraphs are pairwise adjacent. Now, what graph minor theory is interested in is what is the structure of graphs that exclude a given graph as a minor. And we have a very good understanding as to their structure. There's been lots of work done on graph minor theory. So the most basic result you can prove is if you exclude a triangle as a minor, then you're a forest. Why is that the case? If you contain a cycle, you can contract it down to a triangle, and so that's an if and only if relationship, which gives you an exact characterization. Now, if you take any planar graph and you exclude it as a minor, then you're a graph of bounded tree width. I'll define tree width later in this talk, but it essentially means that your graph is like a tree. If you exclude K5, K3 free, this is a classic result that you are a planar graph. This is one of the main results that sort of started off graph minor theory, the fact that there's this connection between this combinatorial property of excluding graph as a minor, and then also this topologicalness of being planar. And then finally, if you exclude any non-planar graph as a minor, then you have a tree decomposition where each torso consists of a graph of bounded genus plus a bounded number of vortices of bounded width plus a bounded number of apex vertices. You either understood what I said or you don't understood what I said. If you don't understand what I said, the takeaway point is we've got a clear picture, we've got a clear structure full of these graphs, and so it's a standard tool in graph minor theory. You're trying to prove something about a class of graphs that exclude a given graph as a minor, use this structure theorem, you go through the different ingredients, and you get results. So probably about like half the papers in graph minor theories tend to go through this structure theorem. So don't worry too much what exactly the structure theorem is. The main point is we know its structure. Okay, so that's 30 years of graph minor theory in 2 slides. Now we're interested in extending graph minor theory to more general classes of graphs. And we're going to be doing that in a coarse notion. Now, this direction was introduced by Georgakopoulos and Papasoglou, this direction of coarse graph theory. And so the goal is, for a given graph H, what graphs have a structure that are kind of like they exclude H as a minor? And so by kind of like they have this core structure that if you sort of view them from afar, it looks like they exclude H as a minor. So this is a very vague notion so far. And so, okay, let's say, what happens here if we say, okay, instead of saying core structure, we say identical structure. By identical, we'll be talking about a isomorphism. Two things are isomorphic if they have identically the same structure. So the idea of coarse graph theory is we want a relaxation of isomorphism, something that kind of behaves like it, but it's a bit weaker. And that's when an important notion from metric geometry comes in play, which is the key definition to understand in coarse graph theory. And that is this definition of quasi-isometry. So this is the main big scary definition for this talk, is a quasi-isometry. So what is a quasi-isometry? Okay, let's start off with what is an isomorphism. It is a map from one graph G to another graph H that preserves all neighborhoods, all properties between G and H. A quasi-isometry is a map from one graph G to another graph H, where distances are going to be roughly preserved. If two vertices are far apart in G, then when they get mapped in H, they're going to be far apart. If they are close in G, they're going to be close in H. So we allow distances to be distorted by a multiplicative and an additive factor. So the parameter, so for an LC quasi-isometry is we allow distances to be distorted by a factor of L and this additive constant of C. And in particular, so from G to H, for every vertex in H, there's going to be a vertex that is mapped somewhere close to it. That's this second condition here. So to try and process and understand this definition, if you plug in L equals to 1, C equals to 0, you run through all the different properties, you're going to get an isomorphism popping out. So this is allowing you to relax isomorphism by having multiplicative and additive distortion. Any questions on this definition? Cool. So throughout this talk, I'm not really going to care what these L and C's are exactly, just that they sort of exist. It'll be quite hand-wavy what exactly they are. They're just going to be floating around there. So let's begin with, okay, what are some basic properties about quasi-isometry? Before that, I should mention that in this definition, there's nothing particular about graphs. You can place graphs by your favorite type of metric spaces. I don't really know of any other types of metric spaces beyond graphs that I really care about, but if you do care about other types of metric spaces, quasi-isometry applies to them as well. But yeah, I presume we're all graph theorists here, so we don't care about that. But yeah, so let's talk about some basic properties. So first is a equivalence relation. If a graph G is quasi-isometric to a graph H, then H is also quasi-isometric to G. You just do the obvious map, and this is pretty easy to show. Next is composition. If a graph G is quasi-isometric to a graph H, and then H is quasi-isometric to a graph J, then G is going to be quasi-isometric to J. That's pretty easy to show. The multiplicative distortion sort of multiply and add up together. You just have to run the numbers, but it's pretty simple.
So it's, yeah, but only with these numbers this actually makes sense because any two graphs are quasi-isometric. Any two finite graphs are quasi-isometric given some large constants.
Yes.
So,
yeah, so for finite graphs, everything is technically quasi-isometric. This notion is more interested when you're talking about infinite graphs, or in my cases, you're talking about a graph class. And so then when you're talking about a graph class, you want the parameters to just depend on the class of graphs rather than on the individual graphs. So that's an important thing to be aware of in the back of your head. So let's do some examples of quasi-isometries, just to get some intuition as to how you might find quasi-isometries between things. So the first is taking a power. take a graph G, and let's say you're taking a fixed power of it. Let's say you take the square. Then if you're thinking about distances in your graph, you have two vertices. The length of the shortest path between them is really only going to go about half the length now after you've taken the power. Once you've taken the power, two vertices aren't going to become more further apart. So that means the graph is going to be quasi-isometric to its power. And you take the obvious map that every vertex gets mapped to itself. Quasi-isometry is also good for subdivisions, so long as you're subdividing each thing just a fixed amount of length. Because now you're stretching the distances between any pair of vertices by a factor of at most k. Quasi-isometry is also good with contractions, so long as what you are contracting has a bounded diameter. So you have your graph, you take disjoint balls of bounded radius, you contract them, you're going to be quasi-isometric to this new graph. You brought things closer together, but only by a multiplicative factor. But the annoying thing about quasi-isometry is it's bad under deletion. So here we have
the bounded radius. The bounded radius could be in the whole graph, not necessarily just in the branch set, right?
Yes. So there's a question when talking about distances. Are you talking about distances on the graph induced by the set of vertices, or are you talking about distances in the whole graph? And so in general, we care about distances in the whole graph. But I guess for this, either works. But yeah, so this property is not hereditary. So here we have an apex grid. Between any pair of vertices, there's a path of length 2 through the apex vertex. However, when you delete that vertex, now you've got a grid, now you've got vertices that are very far apart, and they're not going to be quasi-isometric to each other. So that's a bit of bad news for quasi-isometry and its behavior. Okay, so let's zoom out. So in coarse graph theory, we're trying to understand what graphs are quasi-isometric to H-3 graphs. Now, whenever you're trying to build a theory related to graph minor theory, the starting point is always tree decompositions. You always try and start there, and then you build up from there. And so what I'm now going to be talking about is what is the right notion of coarse tree width? Is there and what is that notion? Can I just get a show of hand? Does anyone here not know the definition of tree width? Okay, everyone knows the definition, so I'll quickly skip over this slide. What is it? You have a graph. You represent each vertex as a subtree of another tree with the requirement that if tree vertices are adjacent to the graph, then there is a common bag that they share. And the treewidth is the best that you can do, -1. The -1 is there so that a connected graph has treewidth equal to 1 if and only if it is a tree. This should be general knowledge and in this audience, and hopefully you guys should all understand that treewidth is a very important parameter in structural and algorithmic graph theory. Okay, so we have tree width. We want to understand what is a right notion of coarse tree width. And my claim is that KD-centered tree decompositions is where it is at. So what do I mean by KD-centered? So we look at a set of vertices. I'm going to say it's KD-centered if we can partition that set into K parts, where within each of these parts, any pair of vertices within that part is at distance at most D within the graph. So you have a set partitioned into K parts. Within each part, things are close together at distance at most D. And we say a graph, a tree decomposition is a KD-centered tree decomposition if each bag is KD-centered. Cool. So the theorem that I would like to talk about is that KD-centered tree decomposition is the right notion of coarse tree width. So what does this theorem say? If a graph has a KD-centered tree decomposition, then it is quasi-isometric to a graph of bounded tree width. Conversely, if you are quasi-isometric to a graph of bounded tree width, then you have a KD-centered tree decomposition. So KD-centered tree decomposition captures what it means to be quasi-isometric to a graph of bounded tree width. There is some distortion of the parameters where you go up by a factor of 2 for my result. I should mention that independent of my work, Tung Nguyen, Alex Scott, and Paul Seymour, they prove the same theorem, but they get a tight bound. So I go from KD-centered tree decomposition to graph of tree of at most 2k minus 1. They go from KD-centered tree decomposition to tree of at most k, and they prove that their result is best possible. Now, so is this actually useful? So I should say in coarse graph theory, there's been many results. The proof in those results are quite long and technical to show. There's a lot of like annoying case analysis where once you now have a tool like this, it makes proving things about coarse graph theory a lot easier because you just have to construct this KD-centered tree decomposition. Constructing quasi-isometry can be a lot more messier to do. This is good news for coarse graph theory. So in particular, using this theorem, I'm able to prove the following, that each of these graph classes are quasi-isometric to a graph of bounded tree width. Now, some of you here may recognize some of these definitions, and you may not recognize all of them. I'm not going to go through what they all are. But the first three, they follow pretty much straight from the definition. There's a little bit of work to do, but it's quite easy to show that if a graph has a bounded range width, then it has a KD-centered tree decomposition, just doing the obvious things. These last two results, so they follow from a, I should also remove the plus because the paper appeared on arXiv yesterday. But we prove a coarse balance separator type result, and so if you have this balance separator consisting of a bounded number of balls of radius 1, and you exclude a complete bipartite graph as induced subgraph, you can sort of show that you're quasi-isometric to a graph of bounded tree width, and proving a coarse version of this classical balance separator result. I'll be a bit hand wavy as to what's all going on there, but once you have that characterization, this tool, you can use known results to deduce these two properties. And so as a consequence of all of this, it implies that each of these graph classes have bounded asymptotic dimension and bounded Sunagata dimension at most 1. Again, I'm not going to define what asymptotic dimension and Sunagata dimension is, but it's a notion from coarse geometry about what is the dimension of the metric space. That people are quite interested in. So having a KD-centered tree decomposition is very useful. Now let's go back to the theorem. So in terms of proving it, there's two directions. KD-centered tree decomposition implies quasi-isometric to a graph of bounded tree width, and the converse, quasi-isometric to a graph of bounded tree width implies KD-centered tree decomposition. So the first direction is the main part of the proof of interest. The second direction is easy to show. You just do the obvious trick, well, do the obvious thing. It doesn't work exactly, but you do the next obvious thing, and then it works and fixes it. So the thing we're going to be talking about is showing if a graph has a KD-centered tree decomposition, then it is quasi-isometric to a graph with bounded tree width. Okay, so let's go through the proof. So we have a graph of a KD-centered tree decomposition. Let's think about a bag of the tree decomposition. So it has a partition into K sets where any pair of vertices in the same sets are close together in our graph. So what we're going to do first is we're going to clickify our graph by each of these parts. We're going to turn it into a click. So now each bag is going to be the union of K clicks. And this new graph that we obtain, we're going to be quasi-isometric to it because we're only adding edges to vertices that are close together. That's not going to change the metric of the graph substantially. It's going to bring things a bit closer together, but only by a multiplicative factor. So we're allowed to do this. So now we can assume that each bag is just a union of k clicks. So what structure does having k clicks give you? A union of at most k clicks. So in this case, the independence number of a bag is going to be at most k. So if you take a maximum independent set in a bag, you can only take one vertex from each of the clicks. You can't take two vertices from the same click, because then they're adjacent. So that means we have a tree decomposition where each bag has independence number at most k. Now this topic has actually been, these type of tree decomposition has actually gained a lot of recent attention under the name of tree independence number. So let me just briefly talk about tree independence number. So the tree independence number of a graph is a minimum k such that you have a tree decomposition where each bag has independence number at most k. Now there's two useful properties about tree independence number for my purpose. The first is it's closed under contraction. If a graph has tree independence number at most k, and then if you contract some edges, the tree independence number does not go up, it can only go down. So roughly, why is this the case? You can think of the same property for independence number of a graph. So you start with a graph, you contract some edges, and then you get a graph H, which has independence number at most k. Let's say it has an independent set of size k. You can then lift that back to your original graph G and then find a independent set of size k. So the independence number can only go down when you contract edges, and that also holds in the tree independence number setting. So yeah, so this is quite easy to show the proof for it. But what is more interesting and is less known is if a graph has tree independence number at most k, you can then true color the graph such that each monochromatic component has diameter at most bounded, some function of k. And diameter is going to be given with distance with respect to the graph as a whole. So this type of result is useful when proving stuff about asymptotic dimensions, and you can essentially use this to prove that graphs of bounded treewidth has asymptotic dimension at most 1. So that's where this type of result come into play. But we have these two properties. Let's use them to finish off the proof. So our graph, we're quasi-isometric to a graph of bounded tree independence number. I'm going to take this true coloring of my graph, such that each monochromatic component has bounded diameter, and then I'm going to contract each of these monochromatic components to obtain a new graph H. And at this point, I'm going to claim that we're done, that we have now constructed the graph H, that we are quasi-isometric to, and that H has treewidth at most 2k. Okay, so why is this the case? H is obtained from this true coloring, and then we contract each of the monochromatic components. So it's a bipartite graph. So that's the first property. And tree independence number is closed under contraction. So we start with a graph with tree independence number at most k. We've done some contractions, and so the graph that we obtain H also has tree independence number at most k. So each bag induces a bipartite graph with independence number at most k. So how many vertices can be in a bag? That isn't a rhetorical question, so.
Most 2k.
Yeah, thanks, Freddie. Each bag can only have at most 2k vertices, because it's a bipartite graph where each side of the bipartition has at most k vertices.
Can you repeat after contraction, which decomposition do you consider?
Same tree decomposition, but the main thing is tree independence number is closed under contraction. So we know that it has tree independence number at most k, and it's bipartite. So just those two properties implies that each bag has at most 2k vertices in it. And because we're only contracting parts of bounded weak diameter, we are then quasi-isometric to this new graph that we obtain. Are there any questions about this proof?
So I have a question. Like in this proof, you get a graph with a treewidth that depends on k, and the quality of the quasi-isometry depends on both k and d.
Yes.
Is it possible to get that the quasi-isometry is only dependent on d and not on k?
Yes, it could be possible. Not with this proof technique. I don't see how. And so I guess, yeah, so this proof doesn't require much work. All the work is basically done by this lemma, and so that lemma is done by induction on k. Yeah, and Paul, Alex, and Tung, they proved that independently, and that was their result independently, and that was all by induction on k as well. So, yeah, that's a nice problem in terms of can you strengthen it to make it just dependent on d, but we don't know. Okay, so this is some good news for the tree width analog in coarse graph theory and looking at coarse tree width. So now going to be moving away from tree width and thinking more about more general graphs, excluding them as a minor. So, okay, what is the goal of coarse graph theory? We want to show for every graph H, we want to characterize graphs that are quasi-isometric to a graph with no H minor. And so we need to try and think, okay, what could be some candidates of what graphs could be quasi-isometric to graphs with no H minor. And one thing that would pop out when thinking about this are induced minors. So what is a induced minor? It's defined in a similar way to minor by a minor model of our graph, with the restriction that if two parts, if there's not an edge between them in our graph H, then they're going to be anti-complete in the minor model. So here we have two branch sets at the top and the bottom. We're not allowed to have any edges between them because there's no edge in the one subdivision of K4 between them. And so a conjecture about, from Georgakopoulos and Papasoglou is for every graph H, an integer R, every graph that excludes the R subdivision of H as an induced minor is quasi-isometric to a graph that excludes H as a minor. So this is a belief, obstruction to, a sufficient condition to being quasi-isometric to a graph H as a minor. I should say they stated their conjecture in terms of fat minors, and so the fat minor version has been disproven by Freddie, myself, James, and Rose. It's still open for various cases. I'm not going to be talking about fat minors because that's a bit confusing to people, and also be talking a bit more about induced minors later in this talk. But this is what we believe to be a sufficient condition that is still open for being quasi-isometric to an H-3 graph. So this is one of the bigger conjectures now in coarse graph theory. I should also say the conjecture about fat minors, excluding a graph H as a fat minor, reduces down to this conjecture if you just care about hereditary graph classes. They just become equivalent. I can explain that after the talk if you are more interested in that. Okay, so we talked about excluding a planar graph as a minor and sort of like tree width. So now let's think about graphs that may be quasi-isometric to planar graphs. And so according to this conjecture, we should think about things that exclude the one subdivision of K5 and the one subdivision of K33 as induced minors. And there's actually a well-studied class of graphs that do exclude those graphs as induced minor. Those are string graphs. So a string graph is an intersection graph of curves of a plane. So we have a collection of strings, and so you can see that the red string and the string graph is the graph on the right. The red string intersects the black string, so the red and black vertex are adjacent. And so a classic result about string graphs is they exclude the one subdivision of K5, the one subdivision of K33 as an induced minor. This is a nice exercise to show. Essentially, you prove it by contradiction. Let's say it does contain the one subdivision of K5 as an induced minor. You can then build a planar graph that contains K5 as the minor. You get a contradiction there. So this is a well-known property about string graphs. So an exciting result from James Davies is actually every string graph is quasi-isometric to a planar graph. So string graphs are a very important class of graphs. They're very dense, and yet they can all be, globally, they look like planar graphs. So with James and Marc Distel, we've been able to extend this theorem. It still has not yet appeared but I know James is prioritizing getting it written up. Apparently, the last update I heard is he's got a bad draft completed, so hopefully there'll be a good draft completed in the near future. We're able to extend this result to region intersection graphs. So what is a region intersection graph? We say a graph G is a region intersection graph over a graph H. If there is a collection of connected subgraphs in H that correspond to the vertices of G, such that if two vertices are adjacent in G, if their corresponding connected subgraphs overlap in H. So, okay, if you aren't familiar with this definition, it's helpful to think about it via string graphs. So if you take your string graphs, you do the planarization by adding vertices at the intersection points. You can then think of a string graph as being a rig over a planar graph, where your connected subgraphs, I guess, correspond to your strings beforehand, and then two strings that are adjacent if their corresponding connected subgraphs overlap. So rigs are a way to generalize string graphs. Are there any questions about this definition of region intersection graphs? As I'll be talking a fair bit more about it, and if there's any point in clarification, that'll be a good point to ask.
So, what is the relation of region intersection graphs to string graphs?
A graph is a string graph if and only if it is a region intersection graph over a planar graph. Yeah. And now we can generalize that, so replace planar graph by KT minor free graph. And so the observation about region intersection graphs is if you are a region intersection graph over an H minor free graph, then your graph excludes the one subdivision graph of H as an induced minor. You just take your proof that string graphs exclude one subdivision of K5, one subdivision of K33 as induced minor, and then it generalizes to prove this observation. It isn't anything too hard to do. Cool. And so the theorem that we're able to prove for region intersection graphs is that if a graph is a region intersection graph over a KT minor free graph, then you are quasi-isometric to a KT prime minor free graph. So we're able to go from T to a T prime. We don't think that the T prime part is necessary. We can just go from T to T. The issue actually, so this proof just goes through the graph minus structure theorem, and we believe that we can get all the constants in the graph minus structure theorem to correspond to just our quasi-isometry, not to our target graph. But our main issue actually comes from the string graphs, and the exact result that pops out of there doesn't go as nicely for the rest of the graph minus structure theorem. So okay, so now zooming out a bit from region intersection graphs and thinking about their relationship to induced minors. I'll just go back. So we had the observation before that if you're a rig over a KT minor free graph, you exclude some graph as an induced minor. But could the converse hold? Could it be possible that if you exclude a graph H as an induced minor, then in fact you are a region intersection graph over some KT minor free graph, where T just depends on your graph H. So this was a question circulating in the community. We was able to find, I guess, two different people who conjectured it or asked the question, Daniel Lokshanov and Rose McCarthy. But there's been a lot of people sort of interested in this, because if this conjecture question is true, it would be amazing. It will imply lots of different things about the structure of induced minors. So, for instance, I know Martin is in the audience, and so this would imply that if you exclude a graph H as an induced minor, then you are Berling bounded by known results. And so people in chi-boundedness would very much be happy if this was true. But unfortunately, this is false. So with Édouard Bonnet, we're able to show that for every integer t, we can find a graph that excludes the one subdivision of K6 as an induced minor, but is not a rig over any KT minor free graph. So unfortunately, we can't lift what we know for region intersection graphs to induced minor free graphs in general. And to finish off this talk, I'll be talking about the construction and proof for this result. But is there any questions about this problem? Okay. So let me move on to explaining what is our construction for proving this result. So on the left, we got the apex grid. On the right, we have what is called the Davies-Pahota construction. So it's many pairwise anti-complete paths with many high-degree vertices adjacent to each of the paths. So how do we construct our graph? So we start off with the apex grid. We're going to take the one subdivision of it, and then we're going to take many disjoint copies of it, and then we're going to order those disjoint copies, and then place that ordering at the top of the Davies-Pahota construction. And if we do this ordering carefully, the graph that we obtain is going to exclude the one subdivision of K6 as an induced minor. So how do we go about actually ordering these things well? Just being a bit hand-wavy, but we're going to do taking a Hamiltonian path over a correct corresponding supergraph of it. So why is this a K6 induced minor free? Well, it follows from the fact that the apex grid that excludes K6 as an induced as a minor. So planar graphs are K5 minor free at an apex vertex, it's going to be K6 minor free. And so if we're able to order them appropriately at the top and many disjoint copies of the one subdivision, following like a Hamiltonian path, what we can argue by contradiction is if the graph on the right does contain the one subdivision of K6 as an induced minor, we can sort of project it up to the very top part find K6 as a minor in a apex grid and get a contradiction. So this extension of the Davies-Pareto grid seems to be a new way to go about constructing families of graphs that exclude a given graph as an induced minor. So does this construction roughly make sense? I'm not going to explain how to do the exact vertex ordering, but if you are careful, it works. Okay, so this is going to be our family of graphs. And so they exclude K61 as an induced minor for any number of choices of path, however big we want the grid to be, and however many disjoint copies we want to take. So let's think about the graph minor structure theorem. So in each torso, we have a bounded number of apex vertices. So in particular, for each torso, if you know graph minor theory well enough, essentially, hopefully you can convince yourself that for every torso is going to exclude k disjoint copies of the apex grid as a minor. So essentially for each torso, because there's only a bounded number of apex vertices we can use, we can't pump too many disjoint copies of apex grid within a single torso. Yeah, so I don't know of any clear citation for this, but if you just plug various results in graph minor theory together, you can essentially deduce this observation as to what does a graph minor structure theorem give you. Okay, so each torso excludes many disjoint copies of a large apex grid as a minor. So what we want to do is just, if our construction is a rig over a KT minor free graph, we want to force many disjoint copies of the apex grid within a single torso. And so the way we do that is we use these Davies-Pareto paths. And so what these paths gives us is for any true vertices in our apex grid, we know that there are many vertex disjoint paths between them that are internally anti-complete to each other. So if this graph on the right is a rig over a KT minor free graph, then true vertices in the apex grid parts, they can't be separated by a small set of bounded independence number, because there's a huge number of anti-complete paths between them. So what these paths allow us to do, it allows us to force many disjoint copies of the apex grid, the one subdivision of it, within a single torso. And this is as a region intersection graph. But we know that each torso, we can't fit too many disjoint copies of large apex grids within them. So arguing things carefully, we can get a contradiction to show that this graph is not going to be a rig over a KT minor free graph. As long as we make the number of paths, the grids, the number of disjoint copies as large as we want, which we can do. That concludes my presentation.